October 1943. High over the North Sea, the sky is a dull sheet of gray metal, and a young American aerial gunner is watching a German fighter break away after its third attack run. The enemy aircraft, a Focke-Wulf 190, peels off cleanly, unharmed, exactly as the last two did. The gunner's twin, 50 caliber Brownings, are still vibrating from recoil. Brass casings clatter into the collection bag. Tracers streak outward in a graceful, glowing arc and carve empty sky. Again, he did everything right. He led the target. He compensated for speed. He held the trigger steady and fired with confidence. And he missed, because the mathematics of deflection shooting are merciless. At 400 miles an hour, the human eye is being asked to solve a geometry problem it was never designed to handle. Angle, velocity, gravity, distance, bullet drop, all compressed into a firing window measured in seconds. By the end of the war, fewer than 1% of American aerial gunners will ever record a confirmed kill in air-to-air combat. But one man is about to change that. The sky over occupied Europe has become an industrial killing floor. Every morning, hundreds of American heavy bombers claw their way into German airspace, climbing to 25,000 feet in tight, defensive formations. They fly wingtip to wingtip, bristling with 50 caliber machine guns, each aircraft relying on the next for survival. The doctrine is simple: mutual defense through overlapping fire. On paper, it is flawless. In practice, it is failing. Luftwaffe fighters attack with ruthless efficiency. They close to 300 yards, sometimes less, fire a short, brutal burst, then break away in sharp scissors maneuvers that leave gunners chasing ghosts. The closing speed is obscene. A Messerschmitt Bf 109 at full power can generate nearly 600 miles per hour of relative velocity. That gives a gunner perhaps 2 seconds. 2 seconds to see the threat. 2 seconds to estimate range. 2 seconds to calculate lead. 2 seconds to fire. Most never connect. The weapons themselves are magnificent. The Browning M2 is a masterpiece of industrial violence, capable of firing 600 rounds per minute. Each bullet weighs nearly 2 ounces and can tear through an engine block if it hits. But hitting requires deflection shooting, a discipline that demands the brain instantly calculate angles, speed differentials, and ballistic drop while the aircraft itself is moving through turbulent air. The Army Air Forces train their gunners as thoroughly as time allows. They fire at moving targets on ground ranges. They memorize lead angle charts. They study diagrams showing where to aim depending on approach vectors. None of it truly prepares them. Combat happens at altitude, where the cold burns exposed skin, oxygen is thin, and fear makes fine motor control unreliable. Post-mission analysis tells the story bluntly. Gunners are expending thousands of rounds per confirmed kill. Entire ammunition loads are burned without a single effective hit. It is not a failure of bravery. It is a failure of geometry. The human eye cannot accurately judge range at these speeds. Depth perception collapses beyond a few hundred yards. Gravity drags bullets downward over long distances. Air resistance slows them. The bomber itself is moving, vibrating, yawing under stress. Engineers try to help. Ring and bead sights are refined. Tables are updated. Training protocols are rewritten. But the math remains too complex, and the time window too small. And the cost of failure is measured in burning fuselages. By the autumn of 1943, the 8th Air Force is losing bombers faster than factories can replace them. Entire groups are shredded over Schweinfurt and Regensburg. Long-range fighter escorts are still limited. Deep inside Germany, the bombers fly alone. Their only defense is their guns. And the guns are not enough. Somewhere inside this mechanical storm, a staff sergeant named Louis Pessa is beginning to notice something that others have missed. He is not a theorist. He is not an engineer by title. He is a gunner aboard a B-24 Liberator. And he has spent enough missions watching his tracers miss to understand that something fundamental is broken. Louis Pessa grew up in rural Wisconsin, the son of immigrants who worked land that rewarded precision and punished waste. Tools mattered. Measurements mattered. If something failed, you fixed it. If it could not be fixed, you built a better version. Before the war, Pessa worked in a machine shop. The job demanded exactitude, tolerances measured in thousandths of an inch, components that either fit or failed. He learned to read blueprints, Visualize three-dimensional systems from flat drawings and think in terms of forces and vectors. It was not glamorous work, but it taught him how machines behave and how they fail. When the draft came, he did not resist. He was sent to gunnery school, where he performed well not because he had a natural talent for shooting, but because he approached the weapon as a mechanical system. He studied ballistics. He compared training exercises with combat footage shown in briefings. The discrepancies were obvious. Combat did not resemble training. His first missions over Germany were exercises in frustration. He manned the waist gun aboard a Liberator called Devil's Advocate, part of a bomb group stationed in East Anglia. The aircraft was a vibrating steel box filled with noise, cold, oil fumes, and fear. At altitude, metal froze. Fingers went numb. Breath crystallized. When the fighters came, everything happened too fast. Pessa fired. He watched his tracers miss. He adjusted. He fired again. Still nothing. The other gunners fared no better. They filled the sky with fire and hope and saw almost no results. After each mission, claims were made. Intelligence officers nodded. Then the gun camera film was developed and showed how far off most of the shots truly were. Pessa did not blame his crewmates. The problem was not effort. The problem was method. The standard ring-and-bead sight was a relic of slower wars. It assumed the gunner could visually estimate range and lead, then hold that lead while firing. But the human eye is not a rangefinder. A fighter at 400 yards looks almost identical to one at 600, yet the required lead angle changes dramatically. At 300 yards, you might lead by 2 aircraft lengths. At 600 by 5. Guess wrong, and every round misses. Worse still, the sight offered no real compensation for gravity. A 50 caliber bullet drops feet over long distances, but doctrine expected gunners to feel that adjustment instinctively. In reality, it was an impossible demand. So Pessa began taking notes. After every mission, he sketched attack angles. He estimated ranges based on target size in the sight picture. He marked where his tracers went versus where the enemy aircraft actually was. Slowly, patterns emerged. Doctrine taught gunners to aim where the enemy would be, but it ignored too many variables. One night in the barracks, Pessa sat down with a pencil and a notebook and began doing something no one expected of a waist gunner. He started solving the math. Louis Pessa did not arrive at his idea in a flash of inspiration. It came slowly, through frustration, repetition, and arithmetic. Night after night in the barracks, he worked through the same problem from different angles. A 50 caliber round left the muzzle at roughly 2,900 feet per second. Gravity pulled it downward at 32 feet per second squared. Air resistance bled velocity the entire way. At 600 yards, bullet drop was measured not in inches, but in feet. Every variable mattered. Range, target speed, crossing angle, relative motion between gun, bomber, and fighter. The doctrine asked gunners to feel those variables instinctively. Pessa knew better. Machines did not respond to instinct. They responded to math. He realized the core problem was range estimation. If a gunner could estimate distance even roughly, the rest of the problem became solvable. Bullet drop and lead angle were predictable once range was known. The difficulty was translating that information into something usable under combat stress. Charts were useless in the air. Mental calculations were impossible at closing speeds approaching 600 miles per hour. So Pessa did what machinists do when theory isn't enough. He built something. Using scrap metal, wire, and parts scavenged from the base workshops, he constructed a crude but deliberate device. It was a rigid metal frame mounted to the gun cradle, fitted with fixed reference points calibrated to ballistic drop at specific ranges. It looked awkward, ugly, even like a coat hanger welded to a protractor. But it embodied something radical. Instead of guessing where to aim, the gunner aligned the enemy aircraft against a reference mark corresponding to estimated range. The sight forced the correct lead and elevation automatically. Gravity and trajectory were no longer abstract concepts. They were built into the geometry of the sight itself. No guesswork, no instinct, just alignment. When he showed it to the other gunners, reactions ranged from polite skepticism to outright disbelief. One laughed and asked if it was supposed to scare the Germans into crashing. Pessa didn't argue. He asked for one thing, a single mission. His crew chief hesitated. Unauthorized modifications were technically forbidden, But the war was not being won by technicalities. After some persuasion, the chief agreed. If the device caused problems, it would come off immediately. Late November 1943. Cold, clouded, unforgiving. The mission target was Bremen, routine by definition, deadly by experience. Intelligence predicted moderate fighter opposition. Pesa mounted his improvised sight before dawn, securing it with bolts and wire. Ground crew stared at it in silence. The Liberator lifted into the gray sky and droned east toward Germany. At altitude, the cold was savage. Ice formed on the barrels. Breath froze into fog. Pesa flexed his fingers and checked the sight alignment one last time. An hour into enemy airspace, the fighters came. Dark specks at first, then unmistakable silhouettes. Focke-Wulf 190s, 6 of them, diving in pairs from the port side. The formation tightened. A flare popped ahead. The sky filled with tracer fire. Pesa swung his gun. The first fighter was closing fast, nose slightly high, exhaust streaming. Range, roughly 500 yards and shrinking. He aligned the aircraft against the second reference mark on his sight. For the first time, the geometry made sense. He fired. The guns thundered. Brass poured out. Tracers streaked forward, and this time, they didn't miss. The rounds walked cleanly along the fighter's wing route. A bright flash erupted. Cowling peeled away. The Focke-Wulf snapped left and dove, trailing smoke. Pesa didn't celebrate. He was already tracking the next attacker. He shifted reference marks, adjusted for the new angle, and fired again. Tracers converged across the canopy. The fighter's nose dipped sharply and vanished into cloud. The engagement lasted less than 60 seconds. When the Germans broke off, Pesa had fired barely 200 rounds and scored decisive hits on 2 aircraft. No spray, no luck, just precision. Back on the ground, the debriefing was routine until the gun camera film was developed. The footage stunned everyone in the room. The first hit landed at over 500 yards. The second came from an angle most gunners would never attempt. The tracers went exactly where the math said they should. The crew chief stared at the screen, then at Pesa. "How did you do that?" Pesa laid the sight on the table and explained. "Ballistics, gravity, reference geometry." He spoke like a machinist explaining a tool, not a man claiming a miracle. Word spread fast. Other gunners came to see the device. Some dismissed it. Others, men who had watched hundreds of rounds vanish into empty sky, understood immediately. The squadron commander ordered Pesa to brief the gunnery officer. The briefing took place in a drafty Quonset hut over bad coffee and a chalkboard. Pesa explained the theory, demonstrated the sight, and answered questions. When he finished, the gunnery officer asked only one thing. "Can we make more?" Pesa said yes. A competent machinist could fabricate one in hours. Materials were common. No exotic parts. No precision electronics. Just geometry, steel, and understanding. The recommendation went up the chain. The bureaucracy moved slowly. The war did not. Pesa flew more missions with the sight. Each time, the results repeated. He scored hits at ranges other gunners considered impossible. On a raid over Osnabrück, he downed a twin-engine Messerschmitt at nearly 700 yards. Gun camera film confirmed it. Now there was no denying it. Other gunners asked him to build sights for them. He did, working nights in borrowed workshops, tailoring each device to the gun mount and position. Each sight was slightly different. The principle was identical. Estimate range. Align reference. Fire. Hit rates climbed. After-action reports began showing a cluster of confirmed kills from aircraft equipped with the modified sights. A training officer from 8th Air Force Headquarters arrived in early December to investigate. He examined the device, reviewed the footage, then ordered a live demonstration. A target sleeve was towed along the coast at varying speeds and distances. Pesa manned a standard gun mount fitted with his sight. At ranges exceeding 800 yards, his hit percentages surpassed anything previously recorded with standard equipment. The training officer was convinced. He recommended immediate field authorization. Orders would take time, but the idea was already spreading. By January 1944, the idea had escaped containment. Gunners across the 8th Air Force were fabricating their own versions of Pesa's sight, quietly, unofficially, and with increasing confidence. They adapted the math to their specific gun positions, tweaked reference marks, compared notes in mess halls and maintenance sheds. It was a grassroots solution moving faster than regulation ever could. Then came Ludwigshafen. The chemical complex sat deep in western Germany, heavily defended and aggressively protected by fighters. The Luftwaffe responded in force. Coordinated attacks came from multiple angles, fast and close. Early in the run, Pesse's Liberator took damage. One engine caught fire. The aircraft began to lag, bleeding altitude. The fighters sensed weakness. They pressed in. Pesse worked the gun with calm precision, the bomber shuddering beneath him. His sight held steady even as the aircraft yawed. One Focke-Wulf came straight in, head-on, closing at impossible speed. Range nearly 1,000 yards. Absurd by every standard taught in gunnery school. Pesse aligned the reference and fired. The fighter disintegrated. Another attacker followed. Adjustment. Burst. Hit. The German pilots broke off early, something they rarely did. The Liberator limped home on 3 engines. The gun camera footage from that mission spread through command like wildfire. Officers assumed the ranges were wrong. The camera faulty. But the calculations checked out. The Air Force could no longer ignore it. In February 1944, a technical order authorized field modification of gunnery sites based on Pesse's design. It wasn't full doctrine yet, but squadron armorers were given permission to build and install them using local resources. Training officers began teaching deflection principles rooted in his math. The effect was immediate. Hit rates climbed. Fighters began breaking off earlier. Bomber losses declined, not dramatically, but measurably. Enough to matter. Pesse finished his tour in March 1944. 35 missions. Multiple confirmed kills. No wounds. He returned stateside and was assigned to train new gunners. By mid-1944, refined versions of his sight were being manufactured and distributed. Engineers improved the hardware, but the logic remained his. After the war, he went home to Wisconsin. Back to machines. Back to quiet work. He never chased recognition. To him, the sight wasn't genius. It was obvious. The mystery was why it had taken so long. He died in 1993. His obituary mentioned his trade, his family, his steadiness. It did not mention that he helped turn missed shots into mathematics, or that bombers came home because one man refused to accept that missing was inevitable. But the logic endured. Modern fire control systems, computing sites, and automated targeting all follow the same principle Pesse proved in a freezing gun turret over Germany. Human limits can be extended when physics is allowed to help. Wars are not changed only by generals or machines. Sometimes they turn because someone looks at a problem everyone accepts and decides it can be solved.